Welcome to the NEAF Talks podcast, written and presented by the Rockland Astronomy Club. This month's podcast takes us on a deep dive on what we can expect to see in the March night sky. Whether you're a backyard observer with a trusty Dobsonian or a deep sky imager chasing the perfect exposures, you know that the heartbeat of the hobby is at the Northeast Astronomy Forum. I'm thrilled to introduce your guides for today's journey through the stars. Joining us first is our very own Julian Edwards. Julian is a voice actor and a veteran of the night sky. His many years as an astronomy enthusiast has given him extensive knowledge of celestial mechanics and deep sky objects from Messier and Caldwell to NGC and beyond. And alongside him, we have Ilana Mikhailov, an astrophysicist and educator from New York, known for her skill in bridging the gap between complex data and the beauty of the night sky. Julian, Ilana, take it away.
It's February 28th, 2026, and we are right on the edge of spring.
Usually that just means, mud and melting snow.
Yeah, exactly. Mud, confused flowers. But right now, it feels like the entire universe is in this massive state of flux.
It really does. I honestly can't recall a time where the observational side of astronomy, the stuff you can literally see with your own eyes, synced up so perfectly with, a complete theoretical meltdown in the academic journals.
Meltdown is definitely the right word. We've got this massive spring thaw happening in the sky, and the physics manuals are just melting right along with it.
Oh, absolutely.
So for this deep dive, we've got a lot of ground to cover. We're looking at a race against the sunrise to catch a blood moon, a planetary parade that's happening right now, and we also have to talk about why Jupiter is suddenly physically smaller than we thought it was.
And that's really just our local neighborhood. If you zoom out a bit, we have a literal crisis at the center of the Milky Way, where our supermassive black hole might actually be an imposter.
Right, the dark matter theory, which is wild. And on top of that, the James Webb Space Telescope is essentially reading the entire history of the universe backward.
It's a lot of paradigm-shifting source material to get through today.
It is. But our mission for this deep dive is to connect all those dots for you. We want to draw a straight line from what you can see from your own backyard, specifically if you're hanging out here in the Northeast, straight to the invisible physics that are, quite frankly, rewriting our reality.
Let's jump right into it.
Yeah, we have to start with the local sky because the clock is definitely ticking. If you've looked west during twilight this week, you probably know something is up. It looks like a massive traffic jam.
That is the Planetary Parade.
Yeah.
It's an ecliptic gathering. We basically have this incredible lineup of Mercury, Venus, Jupiter, Saturn, Uranus, and Neptune, all just strung out along the path of the sun.
I actually caught Venus last night. You really can't miss it. It's the evening star, right?
Right. It's shining at magnitude -3.8. It just cuts right through all that suburban haze. And Jupiter is up there acting as a beacon, too.
But the others are a bit harder to spot.
Yeah, they're playing hard to get. Mercury is really struggling in the twilight glare. And Neptune, well, you're going to need some serious optics to pull Neptune out.
But the real urgency for you guys listening isn't the planets. It's this coming Tuesday morning, March 3rd. We have a total lunar eclipse coming up, the worm moon.
Yes.
But I want to make this clear. This is not one of those, sit on the patio with a beer at midnight kind of eclipses.
No, not at all. This is extreme sport astronomy.
Extreme sport. I like that.
It is, because it's a horizon skimming event.
Yeah.
The geometry here is incredibly tight. The eclipse is happening exactly as the moon is setting and the sun is rising. They are literally fighting for the sky.
Okay, so walk us through the timing. If I'm here in Rockland County or anywhere on the East Coast, really, when do I actually need to be awake?
So totality, which is when the moon turns that deep, beautiful blood red color that begins at 6:04 a.m. Eastern Time. But here is the major problem.
Okay.
At 6:04 a.m., the moon is only 3.8 degrees above the western horizon.
3.8 degrees. That's basically in the tree line.
It gets worse. Maximum eclipse hits at 6:25 a.m. By then, the moon is at 0.2 degrees. It is visibly sitting on the horizon. And then 3 minutes later, at 6:28 a.m., it sets.
Wow, so you literally have a 3-minute window of maximum totality before the Earth just swallows the moon.
Exactly. And you are fighting atmospheric extinction the entire time.
Which is the thick air at the horizon, right? It dims everything.
Precisely. If you want to see this, you cannot have a building, a tree, or even a modest hill in your way. You need a high vantage point with a perfectly flat western view.
So why does it actually turn red, though? I know everyone calls it a blood moon, but what is physically happening to the light up there?
It's a phenomenon called Rayleigh scattering. It's actually the exact same physics that makes our daytime sky blue. The Earth's atmosphere scatters the shorter blue light waves away, but the longer red and orange wavelengths refract.
They bend.
Right, they bend around the curve of the Earth and project directly onto the moon.
So it's essentially a projection.
Think of it this way. You are seeing the light of every single sunrise and sunset on Earth happening simultaneously, focused like a giant lens onto the lunar surface.
That is a killer visual. Every sunset at once.
Okay.
So while the moon is getting painted red, Jupiter is apparently getting smaller.
Yes.
I saw this headline that said, Jupiter is on a diet. Is that just academic clickbait, or did we actually lose part of a gas giant?
It's a very real correction, and it's massive in terms of precision. I mean, for 50 years, we've been using data from the Voyager and Pioneer probes from back in the 1970s as the absolute gold standard for Jupiter's size.
And we were just wrong.
We were imprecise. A new study published just this February in Nature Astronomy used data from NASA's Juno spacecraft. Now, Juno has been in a polar orbit since 2016, and it used this technique called radio occultation to remeasure the planet.
Okay, pause right there. Radio occultation. How do you measure a giant ball of gas with a radio?
It's actually really clever. As Juno flies behind Jupiter, it beams a radio signal back to Earth. That signal has to pass right through Jupiter's atmosphere to reach us.
And the atmosphere messes with the signal.
Exactly. It slows the signal down and bends it slightly. By timing that exact delay down to the nanosecond, we can map the density of the atmosphere and figure out where the edge really is. We are essentially feeling the shape of the planet using radio waves.
Like an ultrasound for a planet. And the map says it's smaller.
It does. The equatorial diameter is about 8 kilometers, so roughly 5 miles narrower than we thought. And the polar diameter is about 24 kilometers or 15 miles flatter.
15 miles flatter. That actually seems like a lot. Why the sudden change in shape?
It comes down to fluid dynamics. We tend to model planets as perfect solid spheres, but Jupiter is a gas giant spinning incredibly fast. Its day is less than 10 hours long, so naturally it bulges at the equator.
All right, centrifugal force.
Exactly.
It's almost that time of year again. It's almost time for the Northeast Astronomy Forum. It's actually the world's largest space and astronomy expo, and it's basically the ultimate welcoming gateway for anyone looking to take their very first steps into understanding the cosmos. First, let's talk logistics and firepower. It's all happening April 11th and 12th, 2026 at Rockland Community College in New York. And you guys, you're going to hear from actual space veterans. We're talking Apollo Flight Director Jerry Griffin, NASA astronaut Don Pettit, NASA astronaut Robert Hoot Gibson, and NASA astronaut Anna Fisher. Second, if you're an absolute novice, seriously, do not worry. The whole event is incredibly accessible. You can literally just jump right into introductory classes like telescopes for beginners, getting started in occultation science. Oh, and there's a huge expanded kids area too, featuring a Starlab planetarium, daily solar viewing programs, and a really cool Meet an Astronaut event. Finally, the shopping here is just out of this world. It's a massive 90,000 square foot showroom floor packed with over 100 vendors. You can get hands-on with major industry heavyweights like Celestron, Teleview Optics, and Astrophysics, and shop for the whole shebang: telescopes, mounts, eyepieces, binoculars, and even filters. So, whether you want to buy your very first telescope or learn the basics directly from space experts, this expo provides absolutely everything you need to launch your astronomy journey. We hope to see you all there. Keep looking up and start exploring.
Now, back to Alana and Julian.
But the new revelation here is the wind. The zonal winds, those famous Jupiter jet streams, they aren't just surface features like weather on Earth. They penetrate incredibly deep into the planet. They are moving enough dense gas to physically change the shape of the planet's gravitational field.
So the wind is literally reshaping the entire planet.
It's churning it. We used to treat Jupiter as this sort of static fluid body, but it's not. It's fiercely dynamic.
Okay, but why does a 15-mile difference actually matter? I mean, to a layman, Jupiter is still just really big.
It matters because Jupiter is our ruler. It's the calibration tool for the rest of the universe. When we discover an exoplanet orbiting some star 500 light years away, we don't measure it in miles, we measure it in Jupiters.
Oh, I see. We say, that planet is half a Jupiter.
Right. So if our ruler is wrong, our understanding of literally every other giant planet in the galaxy is wrong.
We need a straight ruler. That makes total sense. Okay, speaking of fundamental things we might be completely wrong about, let's move to the center of the Milky Way. We've been told for years now that there is a supermassive black hole sitting right in the middle. Sagittarius A star.
It won the Nobel Prize in 2020. A singularity 4.3 million times the mass of the Sun. We all thought it was case closed.
Except now we have a paper from the RER collaboration saying, well, not so fast. They're suggesting it might not be a black hole at all, but dark matter.
Specifically, an ultra-dense core of fermionic dark matter.
Okay, you cannot just drop fermionic dark matter and keep walking. Break that down for us. What exactly is a fermion?
Fair enough.
Right.
Think of fermions like people on a crowded subway car who absolutely refuse to touch each other. They demand personal space. This is a concept called the Pauli exclusion principle.
Okay.
Things like electrons, protons, neutrons, they're all fermions. The rules of quantum mechanics say they cannot occupy the same state at the same time.
They actively resist the squeeze.
Precisely. Now, normally we think of dark matter as this big, fluffy, invisible halo surrounding a galaxy. But this new model suggests that right at the center of the galaxy, gravity is so intense it crushes these dark matter fermions together. They get packed in tighter and tighter until they hit that subway car limit.
And they push back?
Yes, that resistance, which is called quantum degeneracy pressure, pushes back against gravity.
So instead of collapsing all the way down into a tiny singularity, a black hole, it just starts.
It stabilizes. It becomes this dense ball of exotic matter. There is no event horizon. There's no singularity, just a very, very heavy core.
That is fascinating. But I have to play the skeptic here, because we have observational evidence for the black hole. We see stars whipping around the center of the galaxy at completely crazy speeds.
And that is exactly the problem. The math for this dark matter core works almost too well. It explains the orbits of those inner stars, like the famous S2 star, perfectly, just as well as a black hole does. But it actually solves a much bigger problem at the same time, the Keplerian decline.
Which is what?
Okay, imagine you're on a merry-go-round. The outside edge is physically spinning faster than the middle, right? Well, in galaxies, it's usually the opposite. Stars at the very edge should slow down because they are further away from the gravity at the center.
But they don't. We see them spinning way too fast.
Right, which is exactly why astronomers invented the concept of the dark matter halo in the first place, to provide the extra gravity needed to hold those fast-moving outer stars in.
To keep the whole galaxy from just flying apart.
Exactly. But in the standard black hole model, the center black hole and the outer dark matter halo are two totally different things. In this new fermion model, the core is so massive and extended that its gravity naturally reaches further out. It naturally explains the speed of the outer stars without needing to tack on a separate halo. It connects the center of the galaxy to the very edge using one single physical equation.
Okay, that is incredibly elegant. But again, skepticism. We literally have a picture. The Event Horizon Telescope gave us a photo of the shadow of Sagittarius A star back in 2022. We all saw the glowing donut.
We saw a shadow. And this is where the theory gets genuinely wild. The researchers ran optical ray tracing simulations on this theoretical dark matter ball. And it turns out the core is so dense that it acts as a massive gravitational lens. It bends the background light so severely that it creates a shadow that looks mathematically identical to the black hole photo.
Wait, so the shadow we photographed could just be a mirage?
It absolutely could be.
Is there any way to actually tell the difference? Or is this just going to be theoretical ping pong forever?
There is a litmus test. We need to look for something called photon rings. A true black hole, because it has an event horizon, will trap light in infinite, incredibly sharp loops. You'd see very thin, clearly defined rings within the glowing donut. A dark matter core cannot produce those sharp rings.
So the next generation of telescopes basically just needs to squint a little harder.
Pretty much. And if they look close and don't find those photon rings, we are going to have to rewrite 50 years of physics.
Well, if that doesn't make you feel completely untethered from reality, let's take a look at the concept of time. Because the James Webb Space Telescope seems to be breaking the timeline of the entire universe.
Yes, the chronology inversion. The standard textbook story of the universe goes Big Bang, then you get gas clouds, then stars form, stars group into galaxies, and eventually dying stars create black holes. It's a very neat progression.
But JWST just found these things they're calling little red dots.
LRDs. They're appearing in the very, very early universe, between 600 million and 1.5 billion years after the Big Bang. Now, at first glance, they just look like old, dusty star clusters. But when astronomers analyze the light spectrum, they realize they are actually overmassive black holes.
Overmassive compared to what?
compared to their host galaxies. See, in our modern universe, a supermassive black hole is just a tiny fraction of its galaxy's total mass. But in these little red dots, the black hole is huge. Sometimes it's equal to the mass of all the stars around it combined. They are completely dominating the luminosity of these systems, and they're wrapped in these incredibly thick dust cocoons that hide their X-rays so they only glow in infrared.
But how do you even get a black hole that big that fast? There literally hasn't been enough time since the Big Bang for giant stars to live out their lives, die, and collapse.
And that leads us to the direct collapse theory. The idea here is that the universe actually skipped the star phase entirely. In the early universe, you had these colossal clouds of pristine gas. Instead of fragmenting into millions of individual stars, the entire cloud just collapsed under its own immense weight, directly into a massive black hole.
So you don't grow into a monster. You're just born as a monster.
Born as a seed that is already 10,000 to maybe 100,000 times the mass of our sun. And these things were violent. We used to think of early black holes as passive residents just sitting in the middle of a galaxy eating whatever fell in. But recently we've actually confirmed a runaway black hole moving at 2.2 million miles per hour.
2.2 million miles per hour.
Yes. It was likely ejected from a merger of two galaxies, and it's just plowing through intergalactic gas, creating a massive wake of brand new stars behind it. It's absolute proof that black holes were the active architects of the early universe, driving the structure, not just sitting quietly in the middle.
It totally flips the script. The monsters were there from day one building the house. Okay, let's zoom in from the very edge of time to something much more tangible. Let's talk about the actual stuff of life. We've had some really interesting sample returns from asteroids recently, specifically Ryugu and Bennu.
Those samples have been an absolute goldmine. We aren't just finding basic carbon in these rocks. We are finding ribose, which is the actual backbone of RNA. We're finding complex amino acids. And the isotopic analysis tells us that this stuff formed in deep interstellar space long before our solar system even existed.
Which is incredible. But the real head-scratcher for me in the recent data is Mars. The Curiosity rover found something in Gale Crater that the math says really shouldn't be there.
Right. The February 2026 data. Curiosity found long-chain alkanes, specifically molecules called decane and dodecane.
Which, if I remember my biology correctly, are basically pieces of cell membrane.
Exactly. They are fragments of fatty acids. But here's the thing. Just finding organic molecules in Mars isn't really the shock anymore. We know they're there. The shock is the concentration of these molecules compared to the harsh environment.
Explain that constraint.
Well, these rocks in Gale Crater have been sitting exposed on the surface for about 80 million years. Mars has a very thin atmosphere, so the surface just gets blasted by cosmic radiation constantly. NASA ran extensive radiation modeling to see how quickly that exposure breaks down these specific long-chain molecules.
Yeah, the result was?
They should be completely gone, erased. For Curiosity to find any trace of them left today, the original concentration of those fatty acids 80 million years ago must have been absolutely massive. We are talking up to 7,700 parts per million.
Is that a lot for a rock?
It's astronomically high. It's far too high to be explained by what we call abiotic delivery, which just means meteorites or comet dust falling from space over time. The math simply does not add up for falling space rocks to deliver that concentrated volume of material to one spot.
So if it didn't just passively fall from the sky?
It likely came from the planet itself. Now, to be clear, it is not direct proof of life, but it definitely eliminates the easiest non-biological explanation. It leaves the door wide open for a biological history on Mars.
It really feels like the universe is just teasing us at this point. It's like, here are the building blocks on an asteroid. Here are the suspicious leftovers on Mars. You figure it out.
And that is exactly why we just keep building better tools to look closer.
Which brings us perfectly to our last topic. NEEF. The Northeast Astronomy Forum is coming up on April 11th and 12th in Suffern, New York. And for anyone who doesn't know, it is the biggest astronomy gear show in the world.
It really is. And if you go this year, you are going to step right into the middle of a civil war.
The gear war. I have heard about this. It's basically the purists versus the robots.
That's essentially it. On one side of the convention floor, you have the light bucket crowd. Think of a massive Apertura 88 Dobsonian telescope. It's just a huge tube, a giant glass mirror, and zero electronics. You have to physically learn the night sky, and you have to manually push the scope to track the object as the Earth rotates.
It's kind of the vinyl record approach to astronomy. Like, I want to feel the ancient photons hitting my actual eye.
Exactly. It's a very visceral, pure connection to the universe. You are seeing the actual ancient light with your own retina. But then, on the exact opposite side, you have the SMUT telescopes, things like the ZWO Star S50 or the Celestron Origin.
Now, these are the ones that honestly feel a little like cheating to me. You literally just set it down on the grass, push a button on your smartphone, and the robot just finds the galaxy for you.
Not only does it find it, it photographs it. It uses robotics and live stacking sensors to instantly process the image and cut through light pollution. You end up sitting in your living room looking at a vibrant, full-color image of a nebula on your tablet while the telescope sits outside doing all the work in the cold.
See, that is exactly where I get torn. Part of me says, you didn't earn that view. You didn't freeze your hands off finding it. But the other part of me says, wait, I can actually see deep space color from my massively light-polluted suburban backyard? That's amazing.
And that is the modernist argument. Is it better to have a pure analog experience where you're looking at a faint gray smudge, or a highly processed digital experience where you actually see the structure and color of a galaxy? The barrier to entry with these robotic smart scopes is virtually zero. It opens up the sky to everyone, regardless of where they live.
I guess I can't argue with that. If it gets more people looking up and asking questions, I really can't hate it.
Exactly.
So if we step back for a second and look at everything we've covered today, we started with a local eclipse struggling against the sunrise, and we ended with robots taking pictures of the cosmos for us. What do you think is the through line here?
I think the major theme is that the universe is not the static, solved puzzle we were taught it was. We grew up reading textbooks that said, Jupiter is exactly this big, the center of the galaxy has a black hole, and life is rare.
And now?
Now, we know Jupiter is churning and physically changing shape. The black hole might actually be a dense knot of dark matter. The timeline of the early universe is completely backward. The universe isn't static, it's fluid.
It's a really good reminder that settled science is usually just science we haven't built a better tool for yet. Which brings me to a thought I want to leave you all with. If that shadow at the center of our galaxy isn't actually a supermassive black hole, but just a dense ball of dark matter acting as a lens, how much of our everyday understanding of gravity is just a massive optical illusion?
That is a question that is definitely going to keep me up at night.
Me too. Well, if you are in the Northeast, don't forget to set your alarms for 6 a.m. on Tuesday, March 3rd. Find a high hill, look west, and try to catch that blood moon before the sun steals it from you. Thanks for joining us on this deep dive. Keep looking up.
Clear skies, everyone.
That's all for this month's NEAF Talks podcast. We hope you enjoyed it. Remember, you don't need fancy equipment to enjoy the night sky. Your eyes, a pair of binoculars, or a small telescope can reveal wonders that have captivated humanity for thousands of years. For more information about astronomy events, equipment, and the annual Northeast Astronomy Forum Expo, visit rocklandastronomy.com and neafexpo.com. That's NEAF expo.com. Clear skies, everyone, and happy observing.